Today I'm going to introduce a fully self-designed desktop 6-axis robotic arm that I built from scratch, covering both the mechanical design, electronics, and firmware stack that brings it all together. This is not a pre-built kit. Every CNC part, every PCB, and every control algorithm has been newly designed, iterated, and assembled by me as part of this project. The goal of this project is to create a compact yet capable 6-axis manipulator that can be used for experimentation with motion control, inverse kinematics, and real-time embedded systems. In this video, I'll show the entire development pipeline, starting from CAD design to PCB design, hardware selection, assembly, firmware architecture, and finally motion control and inverse kinematics. In addition to the software and control algorithms, significant effort was dedicated to the mechanical design of the 6-axis robotic manipulator. The objective was to develop a rigid, manufacturable, and modular structure capable of supporting the required payload while maintaining positioning accuracy throughout the robot's workspace. The mechanical design process began with the development of detailed CAD models for each robot link, joint housing, motor mount, and supporting component and on-shape. Particular attention was given to the alignment of rotational axes, bearing mounting locations, and motor interfaces to ensure smooth motion and minimize mechanical errors. Once the 3D design was finalized, detailed 2D engineering drawings were generated for manufacturing. These drawings included all critical dimensions, hole specifications, thread requirements, and assembly references necessary for CNC machining. A key aspect of the design process was the application of geometric dimensioning and tolerancing, or GD&T. These tolerances are particularly important in robotic systems because small alignment errors can accumulate along the kinematic chain and negatively affect the positioning accuracy of the end effector. By applying GD&T principles to critical features such as bearing seats, shaft interfaces, and mounting surfaces, the design ensures that manufactured components maintain the required dimensional accuracy and assembly consistency. Following completion of the CAD models and manufacturing drawings, the components were outsourced for CNC fabrication through JLC CNC. This manufacturing service was selected due to its accessibility, precision machining capabilities, and ability to produce custom mechanical components directly from engineering drawings. For the material selection, Aluminium 6061 was chosen for the majority of the structural components. This material provides an effective balance between mechanical strength, weight, corrosion resistance, and machinability. Compared to heavier materials such as steel, aluminium reduces the overall mass of the robotic arm, which helps lower actuator loading and improves dynamic performance. At the same time, it offers sufficient rigidity and strength for the intended operating conditions. The fabricated components were subsequently assembled into the complete robotic manipulator. The combination of accurate CAD modeling, carefully specified GD&T requirements, and precision CNC manufacturing contributed to achieving the dimensional accuracy necessary for reliable robotic operation. Overall, this mechanical design and fabrication process established a robust physical platform that supports the inverse kinematics, motion planning, and control algorithms developed for the robot. Efforts are also made to maximize the range of motion for each joint as much as possible. Every single axis incorporates a diametric magnet and an absolute encoder, which allows the feedback of linkage angles consistently without the need of re-zeroing upon power-up. Overall, assembly was easy enough on the mechanical as well as some additional soldering, with more care and effort needed in wire harnessing. This is because some balancing between wire movement needs, high current, signal integrity, and reliability are needed. The assembly design is such that the wires should cater to the range of motion, and yet with secure retention so as not to have it get caught and break accidentally. The software and firmware are the more challenging parts of this project, especially on the inverse kinematics solver. More on that later. The electronics were designed in KiCad 6 and fabricated through JLC PCB. The system is split into two custom-printed circuit boards. First is a main controller board adapting ESP32S3 dev kit as well as TMC2209 motor controllers. Then there is a dedicated angular position sensing board for each axis. This modular separation helps simplify debugging, improve scalability, and isolate critical subsystems. The main PCB acts as the central nervous system of the robot. It interfaces with Raspberry Pi as the high-level control, ESP32S3 DevKit C1 as the real-time embedded controller motor drivers, including DRV8825 and TMC2209 power input at 24 volts, step down to regulated 5 volts and 3.3 volts. One key feature of this board is a manual selection switch that allows switching between DRV8825 and TMC2209 motor driver operation. Only one driver type is active at a time, allowing flexibility during development and testing. A major design decision in the revision of this board was a move toward the TMC2209 driver. Compared to the DRV8825, the TMC2209 offers several key advantages. Much quieter operation due to stealth chop mode, higher current control accuracy with improved microstepping performance, better thermal efficiency, and reduced motor heating, advanced current control features such as sensorless homing support, more refined motion smoothness at low speeds, which is critical for robotic articulation. Because of these improvements, the design was respun to better accommodate TMC2209 as the preferred driver for precision motion control. The second custom PCB is dedicated to angular position sensing for each joint. Each axis uses an AS5048A magnetic rotary encoder paired with a diametric magnet mounted on the rotating shaft. This means the robot uses 6 identical encoder setups, 1 per axis. The AS5048A was chosen for several key reasons. It provides 14-bit resolution, allowing extremely fine angular measurement. It supports absolute position sensing, meaning no homing is required to recover position after power loss. It uses non-contact magnetic sensing, reducing mechanical wear and improving long-term reliability. It communicates over SPI, enabling fast and deterministic data transfer. It maintains good accuracy even in the presence of mechanical vibration or moderate misalignment. This makes it especially well suited for robotic joints where precision, repeatability, and durability are critical. For actuation, I have selected NEMA 17-stepper motors with different torque and length specifications depending on the axis requirements. Higher load axes use higher torque variants, while distal joints use lighter configurations to reduce inertia. For axes 1 through 5, I also integrated harmonic reducers, specifically the X17-30A series. These harmonic drives significantly increase torque output while reducing backlash, which is extremely important for precision robotic movement. Axis 6 is left without a harmonic reducer to allow faster wrist articulation and reduced rotational inertia. This combination gives a balance between strength, precision, and responsiveness across the entire arm. The motor noise is a bit higher only in this instance due to the use of DRV8825. Once all mechanical and electrical components were ready, the full assembly process began. Each axis was assembled sequentially and according to the GD&T design intent to ensure proper alignment and torque transmission. Each of the datum and pinhole alignment was thought through carefully to minimize the error to the kinematics calculation. After assembly, each joint was calibrated to a defined zero or home position by means of the diametric magnets as well as absolute encoders on each joint. This step is critical because even small offsets can accumulate into large positional errors in multi-axis systems. The calibration process ensures that both the encoder readings and motor reference frames are aligned before motion control begins. This section shows a speed-up video process of assembling axis 5, with some care taken on the wire routing, and also for the diametric magnet supported on a bearing. A sanity check on the encoder readings before moving on to the assembly of axis 6. Before integrating full system control, each subsystem was tested independently. This includes I2C communication as well as SPI communication protocol. I2C communication was verified between the main controller and peripheral devices, ensuring stable multi-device bus operation. SPI communication was tested between the ESP32S3 and all 6 AS5048A encoder boards. This ensured that each axis could reliably report real-time angular position. Each axis was then tested for controlled movement to specific target angles. This verified step accuracy, direction control, driver switching logic, and mechanical response under load. The system firmware and software stack is written primarily in C++ and Python. The ESP32S3 is programmed using Arduino IDE with a dual-core task architecture. The workload is split across both processor cores. Core 0 handles encoder data acquisition and I2C communication. Core 1 handles real-time motor control across all 6 axes. This separation ensures deterministic motor control while maintaining continuous feedback from all encoders. On the Raspberry Pi, I developed a Python-based control interface using Plotly Dash. This provides a web-based UI accessible over a local network, enabling real-time control of the robot. The interface supports multiple control modes, including direct angular position entry per joint, stepper motor step control mode, motor disable mode for passive position recording, PS controller input for manual joystick-style movement, CSV-based motion playback for pre-computed trajectories, homing sequences to return all axes to 0 position. This makes the system flexible for both manual experimentation and automated motion sequences. In this setup for now, I have disabled the steps entry mode, as the angle entries are much more intuitive for users. In this motor mode page, I can choose to disable motors and also to enable PS controller remote control. The speed of the motors can also be selected to be high or low depending on the needs. The buttons of the PS controller can do the same thing, but we'll leave that to another video, for another time. In the recording mode, it is possible to record joint angles in 2 ways. This can be done by either manual disabling of the current through the motors or by switching to remote PS controller mode. Here I have disabled the motors so as to manually move the joints by hand. The program I have written allows me to record the joint angles into CSV file with a click of a button. Other than joint angles, with the forward kinematics model incorporated, the calculation generates also the resulting coordinate of the tool's centerpoint TCP, as well as the orientation of the end effector. The orientation reported in the CSV file as well as on the user interface are for both Euler angles as well as in quaternions. I can then utilize the recorded CSV file earlier with just a simple drag and drop into this user interface again. With the CSV file loaded, I can then select any of the target recorded earlier to move to. I can also run through all targets sequentially in the CSV file. There will be no pause between each target reached. Do note that I have also written a Python module, as share later in this video, that is able to conduct inverse kinematics calculations outside this user interface separately. This allows for much better runtime, as inverse kinematics does require quite a substantial computing power, and it would be much more efficient to run it on a cloud computing such as Google Colab or on a local PC rather on the Raspberry Pi itself. The Python inverse kinematics module can generate solved solutions in the same format as per the recorded CSV files. Now shown here, I have just loaded another pre-recorded CSV file to run. This contains a list of 20 targets around a 25mm spherical surface. With the harmonic reduction gears on axis 1 to 5, the multiplication in torque is 30 times, with some efficiency lost. While the stall torque and dynamic torque could have been more than comfortable if the max continuous current of 2 ampere was applied in all axes blindly. I have, however, made some optimizations by limiting the maximum allowable current in each axis, so that the heat generated from each stepper are minimized. As indicated in the earlier part of this video, I have written Python modules that supports inverse kinematics computation. This can run either locally on Spider IDE or on Google Colab. 2 main algorithms are implemented in this script for solving multiple targets at one go. First part involves cyclic coordinate descent, CCD, for iterative convergence toward a target position. This then sets a baseline for the follow-up Jacobian-based methods using quaternion representation for full pose control on top of the target position. This customized tool allows computation of joint configurations for a desired end effector position, as well as orientation in 3D space. The target coordinates to solve here is a linear interpolation of a straight line in front of the robot. In this Google Colab work environment, I have loaded the script for the inverse kinematics solver, as well as the CSV file with the desired target coordinates to solve for. Both cyclic coordinate descent and Jacobian quaternions method are used in this semi-automatic script to find kinematic solution. While CCD is highly effective for quickly obtaining a joint angle solution that reaches a target position, it does not directly control the orientation of the end effector. To achieve simultaneous position and pose control, Jacobian-based inverse kinematic solver with quaternion orientation error feedback is utilized, allowing both the position and orientation errors to be minimized concurrently. As the Google Colab example here will take some minutes, I will move over to the Solve sample in Spider IDE before coming back. Running the script on Spider IDE is also easy. It's just a matter of making sure the CSV file containing the target coordinates are in the same folder as the Python script. For a different robot arm, the linkage parameters has to be updated. After processing is done, the output data is stored in another CSV file in the same folder where the Python script resides. There is a date code in the file name so that the generated file is always unique and easy to trace. The CSV output format is already in such a way that this file can be utilized directly in the Robot Arm user interface. Another output is a HTML file that shows the progressive iterations of 4 key performance parameters of the inverse kinematic solver, which will be shown for every single target listed in the CSV file in the following order. First, error of position between tool center point TCP to desired target coordinates. Second, the error of Euler angles between current pose to target pose. Third, the error of quaternions between current pose to target pose. Fourth, the progression of the joint angles through the iterations. In each of the chart, for each target, if the inverse kinematics iterations are working well, we will see the convergence of both positional as well as orientation errors to near zero progressively. The joint angles are also expected to taper off as it reaches near target. However, there are scenarios where target might not get solved, and this can happen on the same target with a different pose demand. This is especially on scenarios where one or more of the angle joints has reached its mechanical limits. There is also an interim CSV file which will be overwritten each time it's being run. This file reveals the results of the cyclic coordinate descent, CCD, inverse kinematics calculation for the first and the last target coordinate. The algorithm will attempt to find the best fit between the two combinations such that either the joints will need the least angular change or the joints are close to home positions. This option is selectable in the script itself. Now at this point, do you still remember the other option where the Python script was running in the Google Colab? This has now managed to reach an outcome after slightly over 13 minutes. Due to heuristic nature of the algorithm in each run, it is possible to get different results each time. This random nature is deliberate so as to allow for opportunistic search for more optimized combinations. As we can see here, of the 16 targets, the first 12 did manage to find a solution in each of them except for the final 4. This can then be followed up on in a few ways such as rerunning the program, shift the coordinates slightly to suit the purpose, or specify the start and end pose in quaternions based on prior proven settings before. After downloading files, we can have a closer inspection at the results. The targets with solutions reach the solution with only a few hundred iterations, whereas the 4 failed targets use up the 3,000 iteration limit, which is suggestive that the inverse kinematic calculation went into loops. On inspection of the error log charts, we can see that the convergence is achieved as expected for the first 12 targets. However, for the last 4 targets, it can be seen that it went into unstable, repetitive state and with no solution obtained. On closer inspection, this can be attributed to axis 5, where the joint angle has reached its mechanical limit and is not able to break out of this loop while trying to move towards the target. On the other hand, as shown in the other run made on Spider IDE on another instance, it was possible to reach a solution where all 16 targets can be satisfied. This is the heuristic nature of this inverse kinematics solver. On my home page, I have set up both web pages on WordPress as well as on GitHub containing the walkthrough of the forward kinematics as well as for the different forms of inverse kinematics solver. In a way, at least for me, writing out and having the code makes it easier for me to figure out the logic and math behind. I hope these pages give some insights to the variety of inverse kinematics possible and how the different kinds of inverse kinematics can provide different solutions depending on the needs. I have the sample invoice kinematics codes available also in the GitHub for easy download and analysis. Each of them will have also a link to my WordPress pages for a walkthrough on the logic at your own pace. Separately from the invoice kinematics solver, the main working files associated with this project are placed in my GitHub and can be found in one of the links below. All CAD 3D and 2D files used in the CNC fabrication are placed in the folder. Most suppliers will be able to fabricate from 3D alone, but will need to refer to 2D for the specific tight tolerances control, GD&T, as well as for threading hole specifications. The assembly step file is also available for reference in the build. For part labeling, you can refer to the diagrams in the README section as well. Shown here is one of the 2D drawings among many others. Aluminium 6061 is recommended as material due to its strength-to-weight ratio. I have also uploaded the assembly step file for reference to the build. All of these CAD were done from Onshape. In the build-up, especially on the subsystems, it would make sense to progressively check the component's functionality and integrity before the full assembly level. There are some codes available here in my GitHub and may be updated over time. This includes the sanity check of an encoder along with the stepper motor control at one axis at a time, as well as a scaled-up check on all the 6 axes simultaneously. Per the README shown, some soldering must be done on the encoder board to have the jumpers set for the SPI communication. The table here also indicated FFC cable length that can be connected in series for all of the 6 absolute encoders. It is a total length of about 1.1 meters of FFC cable used by me in this project work. This is actually the second version made in this project, after improving on the pull-up resistor needs as well as impedance matching in the SPI circuitry. There is also a standalone servo motor control, which can be utilized as part of the CSV file in motion planning. The code for ESP32S3 DevKit C1 is written in C++ and can be uploaded into the device via Arduino IDE. Some related libraries may be required. The main upgrades here with this new robotics project than the previous one are the split of tasks of the 2 cores of ESP32S3. Some tweaks are expected with different robotic systems due to motor speed and angular limits. It is important to disable JTAG in the board setup because we need most of the pins in the hardware configuration. Something I find useful for me is using a PS controller pad to control the robot joints as well as for homing. This adds an additional option on top of the use interface with angular input entries. The disadvantage, however, is the need for an intermediate DOF ESP Dev Kit board to be the middleware. This is due to the fact that ESP32S3 does not support Bluetooth Classic, which is the only way that the PS controller can wirelessly send out the control data. The DOF ESP Dev Kit will then forward the data to ESP-S3 wirelessly with ESP-NOW protocol. More on this in a future video. Both the main controller PCBA board as well as absolute encoder board fabrication files are available here. The full design were done in KiCad 6. The build and manufacturing file is such that some DIY soldering is still expected even after fabrication. The main board allows adoption of DRV8825 as well as TMC2209 with the manual switch settings. I have used both, and I prefer TMC2209 because of how quiet and efficient it is. The disadvantage is the higher costs. The user interface written in Python that is to be hosted from Raspberry Pi is also available here. In case another project would like to use this setup, the robot-related kinematics parameters have to be updated as well. Note that the control and communication from the Raspberry Pi to that of the ESP32 on the main board is via I2C. The advantage of having a Raspberry Pi to run the script and host the user interface as a web page allows for remote access and control. The repeatability of the setup is about plus and minus 5 microns without load. I believe this is only an approximate only because of how sensitive the setup is. I have experienced firsthand and seen how the dial gauge needle do shift with the tapping of the floor or with just door movements. My working table is not rigid enough. I am, however, overall still satisfied with the overall performance and how accurate the positional feedbacks are from the absolute encoders AS5048A and the use of diametric magnets. In this setup, I have tweaked the speed of the actuation such it slows down near the target point, thereby reducing errors from vibration. I have also shifted away from using axle stepper library and am using direct bit masking to control the motor drivers directly. This gives me tremendous flexibility and control over the speed and acceleration of the robot joints. Here is some of the repeatability measurements made. For the cost approximation, some of these parts were with me for quite some time already from previous projects and may not account for inflation properly. As shown here, the total system cost is just under 2,000 Singapore dollars, and unsurprisingly, the main bulk of this cost came from four main categories, namely metal CNC, PCBA, Hormonic reducers, and Raspberry Pi. These four key items makes up 75% of total cost. For anyone who are interested in making something similar and would like to reference your design to mine, I have linked all design files that I have on GitHub in the links below for your studies. I have also linked the affiliated OEM parts below for your ease and convenience. I have spent quite a significant of time in searching for suitable components at economical value. I believe this may also help to serve you as a starting point to research for similar parts for your own needs. This video is really just an introduction to the build-up of the full system. It brings together mechanical design, electrical engineering, embedded firmware, and high-level motion planning into one integrated robotic platform. In future videos, I'll be focusing more on some applications, including improved motion planning, different use cases, and executing real-world tasks. So, there's still a lot to build on top of this foundation, and this is just the beginning of what this platform can do. Thank you very much for watching. See you in the next one.